see how close our averages were. We call the average for data set A approximately 3. What's it come out to? 3.06. We'll go. I'll put up my camera. 3.06, 3.1 if you want to call it 3.1. So it's a little bit to the right, but arguably 3. How about you guys? Data set B? 3.05. So to a hundredths off by a hundredths difference, that's negligible. They're both about the same average. Perfect. So it's Bert and Ernie again. Essentially, it's Bert and Ernie again. Okay. How about sample standard deviation? What's your guys' S? Sample standard deviation? 1.16. 1.16. Okay, 1.16. So on average, they're about 1.16 distance away from, or 1.15 away from average of 3. You guys over here? 1.64. So on average, you guys are about a half a unit further away on average. Now, what's the matter? What's the matter? What's the matter? What's the matter, friends? Oh, so here, question. These guys go in L1. And there it is. All done. Remember, actually, this is a good review. This is a good review, friends. This is a good review. These are your data. They go into L1. Exactly. These are your frequencies or your weights, and they go into L2. That's the first thing to remember. The second thing to remember, this is easy to forget, is make sure when you run one of our stats that you tell it L1, L2. You could put in L1 and L2 and then hit one of our stats and enter. It's going to give you an answer. It's going to say the average is 3, and the standard deviation is probably close to what it actually is. But it's going to be larger in data set A and smaller in data set B. Because if you don't give it frequencies, it assumes that each one is in there one time. So if you don't tell it the frequencies, it assumes this graph. For both of them. This, for data set A, the correct standard deviation is 1.15? 1.16. You guys, 1.64. 1.64. Okay? Let me so far. So now that's by us throwing numbers in and calculating. I think we did a pretty fair job of scaling it. And you could scale it differently. You could make each of these twice as big, 4, 6, 12, 8, 10. The same thing's going to happen. The same thing's going to happen. It's going to scale linearly. But here's why. Now that answers like via a computer computation why. What I did while you guys were working was I did a little bit of a ghetto computation over here. Little ghetto. Hang on a second, I'm going to change the coloring too. 2, 1, 0, 1, 2. 2, 1, 0, 1, 2. Okay. This is a calculation I would never ask you to do manually. But what it is it's the calculation of what Natalie said when she said, what is the standard deviation on average? It's the distance a data point is from the average. So what I did was, on each of these calculations, I took how many data points were that far away from average. So from the top of data set A, there is one data point, the 1, that is 2 down from average. So I count that 1, or excuse me, I count that 2 one time, because there's one data point that's 2 down. I didn't make it a negative, because distance is always positive. If I made it negative, they would all cancel anyway, right? If I made the negatives negative and the positives positives, everything would sum to 0, and that's the whole problem, right? That's the problem with summing deviations from average. You have to look at it non-negatively. Good so far? Okay. There are 4 of them that are 1 unit down. 5 of them that are no units down because they're basically at there. There are 3 of them that are 1 unit down. Or 1 unit up. Now we're going up. 3 that are 1 unit up, and there are 2 that are 2 units up. Summing these frequencies, I got 15, which is probably what you guys saw as your end. And then I just did quick math in my head. I got 13 15ths, and I called that about 0.9. I have no idea if it's right or not, whatever 13 15ths is. Is it close to 0.9? 1.9. Oh, wait. It's going to be less than 1. It's 0.86. 0.86! It's fine. 0.9 is fine. Cool. So that was my standard deviation ballpark ghetto calculation for data set A. Did the same thing for data set B, except I adjusted it for the frequencies. Now, there were 5 data points that were 2 down from average. 4 data points that were 1 down from average. 2 data points at average. Look at the difference there. That's the big difference. Hardly anything's at average in data set B. It's bimodal. 3 data points that were 1 up, and 6 data points that were 2 up. Quick calculation, sum up that numerator, looks like it sums up to about 29-ish, somewhere in there. There were 20 data points in that data set. So that comes out to be 1.5. It's a 50% larger standard deviation than A, which is roughly the same thing that you guys came up with, right? You guys over there were about 1, you guys are about 1.5. Roughly, it's almost the same numbers. But the difference is that you guys were doing a more precise calculation, because you guys were actually basing your average on 3.06 and 3.05, where I was calling it 3. So I was doing very, very ballparky kinds of estimations, but it proves the point. These calculations are done the same way, but there are more data out here in data set B than there are out here in data set A. And because there are more data at the ends, that's going to have to weigh more overall. You're averaging larger things, which means your overall average is going to have to be larger. In much the same way, your project average has to be higher than your quiz average. Because your projects are at 25 points, your quizzes are at 10. The project average has to be higher. It's the same logic, because you're adding larger values. Same thing goes on here. It's just that the difference, and this is what I'm really glad you asked this question. It's a great question, Robert. The difference is that we have to train ourselves to think of standard deviation as an average. Because it is. It's on average how far away you are. On average, a randomly selected data point is further from average here than it is here, because on average, the data points are out here. On the outside versus up here, where on average they're in the inside. You see, I'm going from likelihood now. If I randomly selected a data point out here, it would most likely be here, which is further away from average. If I randomly selected a data point up here, it would most likely be in here, which is closer to average. So by definition, B has to be bigger than A, because on average it's further away. Robert, better?
Yeah, much more helpful.
Good. It probably isn't perfect yet, I'm assuming. It probably isn't perfect yet, sitting perfectly yet. But as long as you can kind of get a visual of as to why it's got to be bigger in that bottom. Ask me more questions if you got them.
I don't.
get a sense of
I'm
what-
trying to understand it 3-dimensionally instead of 2.
Three-dimensionally,
When you're looking at
I can draw bigger.
amounts. I'm just trying to.
I can like draw like how did you like, I don't know how to do it three-dimensionally. I hope that got captured too. Now, I wouldn't know what to do with a third dimension. Maybe that
Gives
is,
it mass.
Just looking at a graph.
You're looking at a.
well, careful. Oh, thank you.
Yeah, you're looking at.
Thank you for that. The problem with doing that, the problem with doing that is,
Yeah.
you might exaggerate the difference. This goes back to the intro to prop stat homework, where if you use one too many dimensions, you actually create an inflated, artificially inflated representation of data. Remember the debt balloons? The debt balloons were representing a linear measure, i.e. money,
Right.
but they were doing it via, they made the diameter the right measure, but they drew a balloon which was two-dimensional versus one,
Okay.
and the exaggerations were squared. If you make it three-dimensional, you run the risk of increasing by that square dimension again.
Okay.
So that's the trick. I like what you're thinking, and I like going to 2, but I think...
That's not quite what I'm saying.
That's not what you're
but-
saying.
No, I'll talk to you about
Okay, that's great. Hopefully this gets you thinking down the right path, though, as far as that goes. Please, JC.
So for future reference, for like a question such as this, when we have one that starts higher in the middle, lower on the other side, lower in the middle, the graph. For future reference, we have to do all of this like calculation?
No.
Or is it safe to say that?
No. Did you hear when I said it? This has higher variance than this, true or
Yes.
false? Half the class said true off the bat. You had it in intuition.
Well, that's because I read it out of the book, though. That's good, not because I knew it.
Oh. Okay.
You saw the answer.
Got it. I respect that. The trick is, I want to make that more intuitive, which is why I went through all of this.
Okay.
I'm thinking of a new video now. I'm thinking of a randomization video where I randomly select data points from each of these and keep track of their distances and keep averages and then watch. And so maybe this makes it, okay, maybe I'm getting to your 3 dimensions here, Robert. If I make a video, I think I can do this in Excel, where I put all these data points out in a row and I randomly select from them using Excel, and then I keep track of the running average of the distances, and you watch the averages change, eventually they'll close on these numbers as they go over time. But maybe that third dimension you're looking for isn't like a depth, it's a transition.
No, that could be, yeah.
I'm going to try that. We'll see if that helps. We'll see if that helps. So we'll animate 15C, right? On, what page is this on? Catch that? 105.
Yeah.
Yes, actually it's 95. There we go. Perfect, got it. Let's just cut the first 10 pages of the damn book out.
I know.
Makes it easier. Yeah, if I animate that using Excel, that might give you your dimension. Because I realize, as I say, as I randomly select data from that data set, that's hard for you guys to vision right now, right? For me, it's like, oh yeah, roll a die. And you're like, what die? It has 15 sides or 20 sides. Well, you don't need a die, you just need a random number generator. So maybe that'll help. I'm gonna try that. And I'll link it to the homework sheet. We'll see what it looks like. Cool, Skylar, go.
On this part of the homework.
Yes!
I don't really understand the Pearson's.
Oh, the P. Okay, hang tight. This is a good question. Is this okay for now? Make some more peace with it, please.
Well, I was just, like, the way, I don't know if it has anything to do with it.
Yes, go ahead.
But like, the way that, like, I automatically looked at that and I, like, thought of, like, the bell curve and the tube standard and
Yes.
simulation and the empirical rules.
Good.
So, like, I don't know, for me, that's just, like, if you think about, like.
Most of your data is here.
Majority, yeah, the majority of your data is there, then that's, I don't know. That's.
I love that. I think it's fantastic, actually, to think of it that way. The connection, it sounds like you've already made it. The connection would then have to be there is close to average,
Yeah.
and close to average means a less distance. Making that connection with the other one being farther on average. It sounds like the connection's already been made.
Yeah, but I was just thinking as far as.
Another way to talk about it. Hey, that's fantastic.
Actually, that's what I.
Did anybody else gravitate towards that as well? Thinking about this being a bell curve, this being like an inverted bell curve, essentially?
Yeah.
A couple of you thought that way? Good. I got no problem with that whatsoever. That's kind of where my mind goes first too, but only because I've been thinking about this stuff for 20 years. I'm trying to go from the ground up with this analysis. I love it though. I think it's great. Skylar, Skylar asked a question. Let me scroll this down a little bit further. We'll leave this one be. Let this process some more. The video might help. We're going to back out to variation homework. So right here, I'll put that video right with this guy. I'll make another bit down here. The Pearson's, what the hell is it called? Second skew coefficient. Don't memorize that thing. Don't memorize it, okay? The only reason I bring it up, and you'll see it maybe if you choose to do an extra credit on the out-of-class exam, is you'll see how Excel actually calculates this thing. There's a command in Excel that actually does the Pearson skew coefficient. What it is it's a construct that, I think his name is James Pearson put together back, I don't know how many years ago, that looks at the difference in the average and the median. Now think about that. Why would we care about looking at the difference between the average and the median? To talk about something called skew. Remember skew? When did we talk about skew? Why did we care about skew?
Because it puts your data somewhere else.
It shoves your data, right? Your data somewhere else. Kate, more please.
That out of all your data, you're going to have a center, and if your average is off to the side of it.
That's what skew technically is defined as. When you have skewed data, your average takes a walk towards the tails, towards the outliers. But the outliers pull the average. The median tends to not care. If you only have one or two outliers in a large data set, the average is going to go chase that outlier, and the median is going to stay put right where it is. So what this does is it looks at the difference between that median and that average. And then it weights it with the sample standard deviation. That's a way of standardizing, okay? It's pretty slick, actually. It's pretty slick. Now the trick is, you get a number based on that. You get a number based on that. The interpretation of that number, the only one I found that's peer-reviewed and resourced, was in this Hildebrand article in 1986. And his view was that anything bigger than 0.2, any value bigger than 0.2 of Pearson's SSC there, the PSSC, is considered great skewness. Great skewness, which means, great skewness means we got to be careful with the average because the average might be pulled towards the outliers, might be given a fall, might be pulling a Jared from somewhere right here, right? Might be pulling a Jared. Right? Okay, so, is your question more how to use the formula or what it's telling you?
Well, I never got the same.
That's okay. Hey, that's okay. Skylar's noticing something. When she tried to crunch numbers herself, she couldn't replicate the exact answers I got. That's okay. Because here's part of the problem. The very first graph I had you guys looking at here, you remember this, don't you?
Yeah.
You remember this? You must have had an older version of that, Skylar. I apologize. I updated the graphs a little bit to make them a little more cohesive. The first thing you have to do, I apologize. The first thing you have to do is pull frequencies off of this chart. Well, it's not inherently obvious as to what these numbers are. You can kind of get a ballpark, though. I mean, they're scaled by 5 over here. You scale by 5. But the trick is, what do you put for these guys down here? Well, some of them are easy. So, 3.2 by 3.75, you're going to put 3.5. 3.75, 4.25, you're going to put 4. Pretty straightforward. How about below 3.25? What are you going to put there?
Well, if it just goes to 0, it'll be...
If you can assume it goes to 0, because it can. Now that's something you might have had to Google. Like LDL levels in adult men, you may have had to know, can it be negative? The answer is it can't, because the way cholesterol is measured is milligrams per deciliter of blood. So it's number of milligrams or amount of milligrams over deciliters. Well, the smallest that can be is 0, if you have 0 in there. So you just pick the halfway point between 0 and 3.25. Which would be 1.6 or something like that, 1.625, I guess. Okay, there's one way to do it. Now, the tricky one is the top one up there, the above 6.75. Now, the trick with this, it looks like I actually got a re-randomized graph for you. I don't have any data out there above 6.75, which is totally fine, so you can ignore that one. Skylar grabbed the graph that did have data, though. So what would you do with that? How would you deal with that data out there at above 6.75? Just so you know, there's no correct answer to this question. How would you deal with it? What would you do? Chuck it. That's valid. That's valid. You could throw that data out. If you're going to do that, though, I may offer a suggestion. If you throw that, I would also throw that. I would also throw that. That way, a trimmed mean, if you will. That's perfectly valid, though, Robert. Natalie?
You could do like a nicer number. Like,
Meaning what?
Meaning like instead of having like 6.75, you could do like 7 or 8 or like.
You could absolutely. You could actually above 6.75. You could keep that at 6.75 and call that 8.
Okay.
You could. I have no problem with that. One other thing you could. Oh, Hattie, let me hear your mind. Go ahead.
You could look up some data and find out the maximum LDL levels.
Go do some CDC, Google it, and see. Okay, what's the highest recorded level of LDL on record? Totally fine. Or you could just say, okay, these are the goofballs, right? I had to go down 1.6 there. I'll go up 1.6 here. Call that the midpoint. So there's all kinds of ways you can deal with it. But I guess my point is, don't get twisted up if you can't mimic my exact result, especially if, unfortunately, I updated the graphs without telling you, which I apologize. You're very, very conscientious. You got it a couple weeks ago, I guess, before I did that. Don't worry about not matching my numbers exactly. It's statistics, gray area. And it gets even more prevalent down here in the number of houses listed. This one gets even more prevalent because these numbers get harder to pull. These are 50 different. If you call that 200 and somebody else calls it 195, you call this, some of the lines disappear too, which is kind of weird. I don't understand that. So don't get too worked up. And part of the point of the discussion of this skewness is that every decision we're making based on skew, every single decision you're making based on that skew is based on Hildebrand's 86 article. Right? Great skewness, in quotes, as Kate chuckled when she saw it. Great skewness, that's fantastic. Because Hildebrand said it was great skewness. Who the hell is Hildebrand? Right? That's the only article I can find. Here's my suggestion. The best thing that I would do, that we should all do when deciding if data is skewed or not, is look at the histograms and take a look. What do you think? LDL? Skewed? Hell no, it's not skewed. If it is, it's minimally and so, Skylar, did you actually calculate the skew on your LDL? What did you get offhand?
I could look for it.
That's okay. Take a peek. Ish. That's okay. I'm gonna look at what I got for mine. Mine down here is about
Yeah, like negative 0.06.
0.06.
Negative.
Negative 0.06. I got 0.03. Guess what they're both about equal to?
0.
0, which means there's hardly any skew at all. And the difference between Robert's answer, my answer, and Skylar's answer, don't recalculate, my friend. It's okay. It's okay. The difference, I guarantee you're starting with either a positive or negative 0.0 something. And that's okay, because that means they're not skewed.
They're below below 0.2. which
They're below
is
0.2, so even
not
Hildebrand would agree. That's not true. Is that fair? You see what I'm getting at, friends? So that's the idea there. And you've given me another thing I should do, which is show you how I calculated that one and put that in the solution. So thank you, Scout, for bringing that one up.
Is the PSCC thing gonna be?
PSSC, no. I put it on the out-of-class part as an Excel command for extra credit.
Oh,
And if you read the solutions that I put down here, if you look at the PSSC for the bimodal,
yeah,
it gives you a number that's less than 0.2.
right.
But no one in their right mind would say that that data is even close to bell-shaped. It's just that the deviations cancel each other out. The average and the median are essentially in the same place, but you shouldn't use either one of them. Does the average and the median actually describe what's going on in this class? We've had this discussion before. No! It's crazy all over the place bimodal. But the average and the median are the same, so the calculation is going to be 0, essentially. Silly, huh? Yeah. All right, you got that glazed look. You go wander around a little bit. Flush some air. Okay, what's up?
I have